Hey everyone, and welcome back for another deep dive. You guys know how much I love it when we get to really peek into the minds of researchers tackling these big brain-bending questions.
And today is no exception. We are diving headfirst into neural networks.
Oh.
But not just any networks.
Yeah.
Networks that can solve problems so complex, they leave traditional computers in the dust.
Okay, I am buckled up and ready. We are time traveling all the way back to 1986 for this one.
Wow.
When a paper by John Hopfield and David Tank basically threw down the gauntlet for artificial intelligence.
Oh, wow.
These researchers were not messing around.
Okay.
They wanted to see if they could capture the magic of the human brain in a model.
Right.
Even if it meant simplifying those billions of neurons and trillions of connections we've got going on up there.
Yeah. You make it sound like they were trying to, build a brain in a bottle or something.
Kinda. Okay,
Right.
Though maybe a model brain in a bottle.
Okay.
Their paper is all about building a simplified model of how neurons interact. And you know me, I always get a little awestruck thinking about the sheer scale of what's happening in our head.
Oh, it's true. The complexity is just mind-boggling. But what's so fascinating is how they managed to simplify things without losing the essence of what makes neurons so powerful.
Yeah.
They zeroed in on a few key features. How neurons take in information, how they process it,
Right.
and importantly, how they respond.
And this is where that elegant sigmoid curve comes in, right?
Exactly.
It's not just a simple on-off switch. It's like a dimmer switch with a whole range of responses.
Yes, exactly. It's that nuanced response that gives these artificial neurons their computational power.
Okay.
And to make it all a little easier to visualize, they used an analogy I think we can all wrap our heads around.
Okay, I'm intrigued.
Electrical circuits.
Okay, break it down for me.
So imagine each neuron as a tiny amplifier with inputs and outputs, all connected by wires that act like synapses.
Okay.
The strength of the connection, how important is this signal factor, is represented by a resistor. It's a clever way to bridge the gap between the biological complexity of the brain and the more structured world of electronics.
So we've got these simplified neurons all wired up like some kind of microscopic supercomputer.
Yeah.
But how do they actually go about solving problems?
Right.
It still feels kind of like magic to me.
Well, it's definitely an elegant solution.
Okay.
One of the key concepts they introduce is this idea of computational energy. It's a mathematical tool they use to track how the network's state changes over time.
Okay, so instead of just like a jumbled mess of signals, we can now visualize the network's activity,
Right.
almost like mapping out the energy of a system in physics.
Exactly. And just like physical systems tend to settle into states of lowest energy, these networks are designed to do the same.
Okay.
That lowest energy state. That's our solution.
So we're looking for the bottom of the hill where everything's stable and the network says, aha, found it.
You got it.
Okay.
But here's where their insight really shines through.
Okay.
They discovered that a very specific type of connection between neurons, symmetrical connections, is absolutely crucial for making this whole energy landscape thing work.
Symmetrical connections. Okay, now you've officially piqued my curiosity.
Okay.
Tell me more.
Think of it like a two-way street.
Okay.
If neuron A is strongly signaling neuron B, then neuron B should be sending an equally strong signal back to neuron A.
Got it.
This creates a beautiful balance in the network,
Okay.
a kind of harmony that guarantees it will eventually settle into that stable solution, that valley in the energy landscape.
Right.
Without symmetry, it's chaos.
Oh, no.
The network's state could just bounce around endlessly, never finding the answer.
So symmetry is like the secret sauce,
Yes.
the thing that keeps these networks from spiraling out of control. It's like they built in a self-correcting mechanism, which is amazing when you think about it.
Yeah, it's very cool.
But let's get down to brass tacks.
Okay.
What kind of problems can these networks actually solve? Give me an example.
Well, they start with an almost poetic example. Associative memory.
Okay.
Imagine you've shown this network pairs of things, like the letter A in the word apple.
Right.
Because of the symmetrical connections, seeing A will trigger apple, and seeing apple will trigger A.
Interesting.
It's a simplified model of how our own brains recall memories based on partial cues.
That's incredibly cool. But I have a feeling they didn't stop there, did they? This is a deep dive. After all, we need something with a little more oomph.
You're right, they didn't stop there.
Okay.
Hopfield and Tank decided to tackle a problem that's deceptively simple to explain, but notoriously difficult for computers to solve efficiently.
Okay.
The traveling salesperson problem.
Oh, I've heard of this one. It's the one where you have to figure out the shortest possible route to visit a bunch of cities, right?
That's the one.
It's like a nightmare for anyone who hates planning trips.
It seems simple enough, but here's the catch.
Okay.
As you add more cities, the number of possible routes grows exponentially. Even with a relatively small number of cities, the possibilities become astronomically large, way too many for even a supercomputer to brute force through in any reasonable amount of time.
So we've got this problem that makes even computers sweat. And the solution is a network designed to mimic brains.
Oh,
Yeah.
you're going to have to explain this one to me.
Okay, get this. Each neuron in the network represents a hypothesis about a city's position on the tour.
Okay.
So one neuron might be saying city B is the second stop,
Right.
while another neuron is claiming city D is the last stop, and so on.
Okay, I'm picturing this massive web of neurons, each one a tiny piece of the puzzle.
Right.
But how do we go from there to an actual solution, like a complete route for our frustrated traveler?
That's where those inhibitory connections come in.
Oh, okay.
The don't even think about it signals we talked about earlier.
Right.
The network uses these inhibitory connections to enforce the rules of a valid tour, preventing any city from being assigned to multiple spots.
Ah, so it's like a self-editing mechanism.
The network is constantly checking its own work, making sure no city is booked twice on the same trip.
Precisely. And here's the real beauty of it.
Yeah.
The network also factors in the distances between cities, which are encoded in the strength of certain connections.
Okay.
It's like the network has an internal map and a strong preference for shorter travel times.
Wait, are you saying this network is basically using its analog nature to explore tons of possibilities simultaneously? That's incredible. No wonder traditional computers struggle with this problem. But hold on, this paper was published in 1986.
Yeah.
What kind of impact did it have back then? Did people realize what a big deal this was?
Oh, absolutely. This research sent shockwaves through the field of artificial intelligence.
Yeah.
Remember, back then, computers were nowhere near as powerful as they are today.
Right.
The fact that a relatively simple network could solve something as complex as the traveling salesman problem, it was a revelation.
It really makes you appreciate how far we've come. So much of what we take for granted today, like facial recognition software or those AI assistants that can practically write poetry, has its roots in this early research.
Exactly. This paper helped to lay the foundation for a whole new era of AI.
Wow.
It showed that artificial neural networks weren't just a theoretical concept. They could tackle real-world problems in a way that traditional computers simply couldn't match.
Okay, I have to admit, my mind is officially blown. We started with a deep dive into the inner workings of neurons, explored the elegance of symmetrical connections, and ended up solving one of the most challenging problems in computer science. It's amazing to think that this research all the way back in 1986 helped pave the way for the AI-powered world we live in today. If you had to distill it down, what's the one big takeaway you want our listeners to remember from this deep dive?
I think the biggest takeaway is the sheer power and potential of neural networks.
Yeah.
Even back then, with limited computing power, researchers were able to demonstrate that these systems could solve incredibly complex problems.
Right?
By mimicking the way our own brains work.
Yeah.
And that's just the tip of the iceberg.
It really makes you wonder what incredible breakthroughs are still waiting to be discovered as we unlock more secrets of the brain. I, for one, am excited to find out. That's it for today's deep dive, folks. Thanks for joining us on this journey into the fascinating world of neural networks.
Thanks for having me.
Until next time, keep those brains buzzing.